Hello, everyone. Today we're going to be looking at data design and management, and that's the book we were assigned. And then in my presentation in this video, I'm going to be concentrating on chapter one and two. So, chapter one basically introduces what data design, management, and research is about, and chapter two basically talks about one of the research challenges. So first off, what is a data center? A data center is a large distributed system that performs parallel computation for different users. So a data center is basically something that can be used to increase the amount of time to increase or sorry decrease the time that it takes for computation to um, complete because of its capability of performing parallel computations. So it's able to distribute whatever computation, whatever task you have to different servers, regardless of where the task is coming from. So that's for diverse users, for different people, and it's able to perform it using parallel computation. So there are two different types. We have the private data center and we have the public data center. Let's look at the private one. So the private data center is usually for people within a single organization, a single entity, and it's the sharing mechanism is usually tailored towards the organizational needs for that for whatever organization it's located in. So, for example, the data center at Bucknell will probably be tailored towards educational needs. So probably only computation that relates to educational processes would receive higher resources, will receive higher priority in such an environment. An example of private data centers could include software as a service, search, mail, things like that. Now, public data centers, usually the users for public data center have no affiliation with the system operator, and you are able to select what resources you receive. An example of this can include Google Cloud and Amazon Web Services. So most of the developers that make use of this product are not necessarily Amazon developers. They don't necessarily work with Google, but they're able to select the resources they want, their programs, they want their task to make use of. What are the objectives of data center design and management? There are two major objectives. One is to be able to balance service quality and energy efficiency. If you look at the two objectives, you see service quality is mentioned in both because that is a given. That's why we use data centers. We want to want to improve the quality of services provided for users. But when doing that, we want to also ensure energy efficiency. So that means using hardware power in a reasonable way, being able to sometimes employ low power servers, being able to understand that, oh, this task can actually be computed at a good rate with low power servers. So let's use that instead of using the high energy power, being able to recognize that can increase energy efficiency because data centers use a large amount of power, and power is not an unlimited resource, it's limited. So it's important that we're able to efficiently use energy. Another important thing which relates to service quality is we want to be able to complete tasks quickly, in tens of milliseconds, especially in today's technological world where we want things in the right moment, the exact moment. So being able to complete tasks in tens of milliseconds is one the sub objective of data center design and management. And also, while getting this good service quality, we want to be able to do it in terms of fairness too, giving priority where priority is due, being able to allocate resources equally. This can also tie into net neutrality, everyone having equal access to the resources. So these are some of the two main objectives of data design and management. So what are the research challenges in data center research? So What the first one, we have about five which we'll talk about. The first one is applications and benchmarks. So data center applications, as with many applications that we've worked with, um, implement multiple abstraction layers. They're usually built on generalizable platforms, and they always have multiple abstraction layers. We can think of this with the high level languages we use today, things like Java, C++. These are high level languages that really hide the inner workings of the computer. But so this, for example, so this data center applications work in the same vein. They do not necessarily give us the inner workings of a data center, but they tell us how well a data center is working. So computer architects can't simply they cannot simply benchmark an application because there are different questions that come with this. So what this is saying is that you can't simply standardize a data center application and get the full story on how the data center works. So you have to, because there are many other questions you have to answer to actually be able to give a full brief, full knowledge of what is going on in the data center. And there are some questions why this is so. Because, for example, consider a Spark application. Do you want to include just the application task, or do you want to include the engine that runs the application? Looking at search too. So what index of documents and what types of queries actually tell us produce a representative benchmark. What types of queries will actually give you the full story of how a data center works. So to answer this question, so computer architects have to always increasingly get a precise measurements from large software systems. So you don't want to pick just any data center application to measure to benchmark a data center. You want to pick a robust one, a large software system that is making use of different aspects of the data center to really tell the full story of how a data center works. Another research challenge that people are studying day and night is design. Design is basically combining service quality and energy efficiency. Uh, um, the full story is that high performance design ensures low latency and high throughput accompanied by a significant power cost. So that's saying you can get high performance without significant power cost. But at the same time, you want to high performance for your users, but you have to consider that you're wasting a lot, not wasting, but you're using a significant amount of power, which is going to cost the system. Not only going to cost the system, it's going to cost in terms of money and time. So you want to find a balance between service quality and energy efficiency. Like I mentioned earlier, energy is not an unlimited resource for, especially for the data center. So you want to be able to manage that. Get have systems that can combine service quality, the amount of quality the amount of service quality you provide for the users, and also how your data center manages energy. Now, management is another research challenge that computer architects are interested in. You have to be able to anticipate the runtime consequences of decisions. So if a data center decides that I want to run this task this way, I want to give this task to this four different servers, for example, it has to be able to know that the part I'm giving to these servers, probably there are parts that can run in parallel. They have to be able to anticipate what are the consequences of partitioning this task this way. So this is part of manageability. A data center has to be able to anticipate these kind of things. Also, it has to be able to manage performance risk and the probability of contention and poor outcomes, especially in shared systems. So there's always the probability that two tasks will be competing for the same resources. So it's important that it's able to understand, okay, when is this going to occur and how am I going to deal with it? And it also, the data center has to be able to also allocate hardware and schedule software for some performance targets and to ensure fairness. You have to balance the two. Ensure fairness by making things equal, but also assign priorities. What are the things that actually go with the organization's needs that just have to be performed? There are these set targets by this organization. How do we meet this quickly and at the same time ensure fairness? These are some management factors that data center research is trying to study. Another one is hardware simulation. So hardware simulation, especially for data center research, is complicated. But it requires from full study, we've found out that to be able to fully support it, you must they must computer architect rely on a sophisticated combination of emulation and simulation. We'll talk more about this in a few other videos. We talk more about hardware simulation, but you need a good combination of these two. So emulation tries to make sure that you have functional correctness, which means I'm putting in something and it's giving me the right thing that I expect. Simulation means you are studying, you have the timing models for greater insight. You're able to see how much time is this taking, what is going on, what are the different values at different times for the system. So this hardware simulation is an important part of research, of data center research. Also, another method that computer architects, excuse me, make use of is they try to identify regions. Instead of having a full simulation of the whole data center, they identify regions that they want to study and just do a full system simulation on that region with different detailed timing models just to understand that region before getting, for example, if they want to study latency time, for example, just concentrate on that, have a full system simulation that only concentrates on that. So that's some way people try to deal with hardware simulation, because normally this is expensive, very expensive under normal systems. Another research challenge is system simulation. So this is also complicated, especially by system scale. So the way we try to deal with this, the people apply, computer architects apply analytical and empirical approaches. Being able to study and at the same time have numbers that back these things up. So when you're assessing a system's performance, you want to be analytical and you want to be empirical at the same time, because it's not usually easy. It's not a very good setting to have physical measurements. You can't have a ruler, for example, to measure these things. So you want to apply different approaches that actually give a full story on how the data center works. Now let's look into one of the research challenges that we talked about earlier. We're going to look at it in full detail now. Applications and benchmarks. Let's start off with this with a definition. What are benchmark suits? So benchmark suits try to find the applications and software targets that give the full story about a data center. And the story behind this is these are usually a combination of applications. One application usually can tell the whole story about a data center. And data center benchmarks are different because they are scale out, they do scale out computation, especially in large distributed systems. And what does scale out mean? So scale out just means being able to trade resources for power efficiency. So you are losing out some resources just to gain more power to continue to so you're probably giving up time for power efficiency, things like that, so that you can have a tightly integrated data center server. So, what are some applications that we make use of to tell us more about the data centers? We have four main ones. We have search, we have memory caching, we have map reduce, and we have graph analysis. Like I mentioned earlier, you want a combination of these applications to really tell you the full story for a data center. So, searching and caching are latency sensitive applications. So they help us know the amount of time it takes in order to guarantee user experience, which is usually tens of milliseconds. Then you want things fast. When you're searching on Google, you want the result immediately. Things like that. Caching, you want your data immediately. So these kind of applications help us to know how fast is a data center working. MapReduce and graph analysis are batch application. So these are things that the computation completes in the background, but are they giving the right results? When are they ready? Things like that. So this combination of applications give us a good read on how a data center works. Now we're going to look at each of them and see how they contribute to data center research. Now search. Now basically what is search? Most of us know how search works. It's basically crawling and indexing content and trying to aggregate and organize the data. Now, I mean, just looking at, for example, Google search is basically crawling through the web, indexing the content based on the queries, and then identifying pages that match the query, indexing it. Sometimes a special part of this Google search and things like that is trying to find relevant scores, ranking the pages that actually are the result of the crawling, trying to rank the pages and displaying those pages to the user. So search, that's basically the definition of search. So this is an example of Microsoft Bing, how Microsoft Bing search works. So queries go into the aggregator and it sends it to different nodes. This is the ranker that tries to do a page rank. We have the neural net that does all the search, put the index and things like that, and then you show the results to the user. This is an example of how Microsoft Bing works. Just having an aggregator with incoming queries, and it tries to, if you see there are different nodes here, so it tries to divide the query depending on the query, trying to divide it between different aggregators to work on them. Different nodes. And the aggregator divides the incoming queries to different nodes to try to work on them and get the results presented to the user. So how do you study search? How do we use search to study data research? So we need you have to use search. We need a data corpus, which is basically a large amount of data. You need queries that will actually exercise the search engine. Queries, users are fond of giving different types of queries. You don't know what the user may put into your system, so you want to give queries that will actually exercise it, and so we can truly get the full story. And also the type of hardware design space. Web search relatively is easy to simulate, so you can easily partition the index across many servers, and then you try to fit the index into memory, and you're able to also simulate end-to-end query execution because it completes in hundreds of milliseconds quickly. Some researchers have been able to simulate web search queries using things like MAS86, SIM2, deploying Apache, Notch, and Lucene, and and most of them use it for Wikipedia data. They execute search queries in Wikipedia's data. The second application is memory caching. Now, just looking at this table gives us representation of disk technology over 25 years. If you look at the disk capacity, we've gotten better, Moore's law at work. We have our disk capacity is over 15,000 times better than it was in the mid 1980s. Unfortunately, the maximum transfer rate, the rate at which we get data from the disk, because the reason we put data in disk is so that they can be used. So you want to be able to access it at different times. Unfortunately, the maximum transfer rate has only increased by 50 times, which is, I mean, comparing them together, having this large data set, but being only able to access it just a little bit, that is a big problem because it limits how frequently data can be accessed. So how do data centers work with that? Because data centers are basically working with huge amounts of data. So what they do is they try to cache popular data. Data that is requested for a lot of times is usually cached by the data center servers. And this has been they found using Zipfian distributions that this actually helps to improve performance at least at a moderate cost. So just storing the data, the popular ones, the way our normal computers work. This is just using most pop the different caching technologies there's least recently used. This is using the most popular ones. Is able to know, okay, how often is this used and is caching it. Some use key value system, assigning keys to different data objects and just being able to access it immediately. So currently, we found that Facebook actually caches 75% of its data in memory. Just to have easy access to this data. So they are already caching, I mean, majority of their data in memory already, just so they can get the advantage of improved performance. So I mentioned earlier that some people are using key value system. An example of that is RAM cloud. So it's a kind of key value store, but it holds all of its data in memory so that we don't even have to use disk, so that we don't face the problem of transfer, the huge transfer time of getting data from the disk. So the case for RAM cloud is based on software trends and hardware limitations. So it's saying this would work for everybody because already data center hold most of their data in memory. So just putting the rest of, but like we mentioned earlier, Facebook already put 75% of its data in memory. So just putting the remaining 25% wouldn't be a lot of work for it. And also because disk is already, disk provides too much problem. If we look at our previous table before, um let's look at the table again. Disk have improved almost 20,000 times better, and our transfer rate is still struggling at 50. So there's this big lag that we just cannot deal with when storing our data in disk. So RAM Cloud is saying put everything in memory already so that we don't face all these disk performance limitations. Because I mean, there's nothing wrong with storing your disk, storing data in disk. It's just be prepared that your disk is slower, basically very slow, especially for data center applications that have to be completed in hundreds of milliseconds. You don't want to waste time just without you're wasting time on actually getting the data to use, not in performing the computation. So it's important that these servers have easy access to the data they require. What are some strategies we use to benchmark caching? The three main queries that you make to store data is you either try to get it, you try to set it, or you try to delete it. So you have to make sure you are able in your simulation or whatever framework you're using to test this. You have to be able to make such queries. So also you have to find a way to get data popularity. We mentioned earlier that data popularity has improves performance at a moderate cost. So you want to find a way to measure what makes a data popular? How do we say something is popular? Also, the data object size is very important. The typical size is small, so this makes it easy to easily also access the data. If they are small, um, uh, this small fine-grained accesses illustrates the memory's caching advantages over disk. So you want to be able to access the data quickly, so you need them in small sizes. Another application that helps us understand data centers is the MapReduce application. So basically, the way, like we defined data centers before, the way they work, they're large distributive systems, distributing computation, distributing tasks to different servers regardless of where the task is coming from. But they have to be able to make sure communication is going on between these servers, especially if they depend on each other for a specific result. So, for example, if you've distributed a computation to four different servers, and maybe server two needs the result from server one, so you have to be able, you have to ensure that these systems are communicating with each other, and so this helps to ensure performance and reliability of data, which is a very important concept. MapReduce is a programming and runtime system. So it's made up of map and reduce. So this try to calculate key value pairs. So basically, the way the system works, it tries to partition input data and then performs map on that, collates the result, and then sends it to the reduce function. We'll look more into that. It tries to ensure resilience by trying to deal with failed tasks very quickly. Once it notices, oh, this part of this is not working, it assigns it to another server immediately. So it's a very good system of good system of utilizing data center um, advantages. So let's look more into MapReduce. So these are examples of how MapReduce functions look. Now looking at map, okay, let's look at an example. So you have a document. For example, let's say you have an essay and you want to know the number of times the word, or maybe you just want to know the number of times each word appears in the document. The first thing you do is the system does is it tries to partition this document into different parts and then sends the different parts to different servers and applies the computation to these different parts. So it counts all the words or the number of times each of the words appear in all of these partitions, and then something we call the master, which we'll look into in the next slide. Let's look at it. Oh yeah, this is it. The master collates the results from the map workers, collect them. So, for example, if each of those partitions, maybe a word called maybe ball, occurs in maybe partition one 10 times, ball occurs in partition two 20 times, ball occurs in partition three 30 times. So what it does is when it sends it to reduce, so the key in this case will be ball, and the values will be 10, can't remember numbers now, but 10, 20, 30 from each of the partitions. So then the reduce now does its work and emits the results. So this master is very important. It gets all the results from the mappers and sends it to the right reduce workers so that we can get reliable data. So how do we study map reduce? Um, so basically, you just I mean, in today's world right now, simulations are able to model RO activity from the master, the worker, and other aspects of the runtime systems. But in the future, we want to be able to target specific map-reduced tasks and try to exclude runtime overhead just to concentrate on just map-reduce. And let me mention this quickly. MapReduce for computer architecture research requires a data set, and you need a sequence of MapReduce tags. That is essential already. But we are able to simulate different parts of the hardware, the master worker, and things like that. We're able to simulate them already. Another application we're going to look into is graph. So, what is a graph? What is a graph? A graph is basically a data graph consists of vertices, edges, and data. Edges connect to vertices. Um, and vertices usually made up of data. So we know, well, we're learning that graphs usually are large and sparse, especially the ones for data center computation. So we wanna this paper, Satish et al. Tries to identify four computational kernels for graphs. We have PageRank, breadth first search, triangle counting, and collaborative filtering. So these four help us understand graphs more, and they are basically representative of what people do with graphs, why we use graphs essentially, and their advantages. So let's look at each and every one of them. So PageRank, first off, this helps to identify popular graph vertices. And the way you get the page rank for a particular vertex is based on what are the ranks of its neighbors. So the rank of each of these neighbors, and it does this iterative, it does it through different iterations. Sorry, two different iterations. So the page rank of a particular node is based on its neighbor. So something like page rank it would be useful for search algorithms, being able to rank your different pages and determining what you show to the user. Another one is breadth first search. This is a classic graph traversal algorithm. Helps to know the minimum distance between a starting vertex and the other vertices in the graph. This is when we think of things like Dijkstra's algorithm, things like that. These are um the shortest part between and things like these are just inherent in graphs. You want to know the distance between different nodes. So the traversal can be, you can go from top to bottom, you can go from the bottom to the top, or you can have a mix of both. So these are important computations for graphs. And the way you do this breadth first search is you first initialize the distances to infinity, and you try to calculate the distance. This also requires multiple iterations. The third representative computation for graph analysis is triangle counting. So this just tries to count, okay, the number of triangles in the graph, which is, and what is a triangle? A triangle is when two vertices have a third vertex as a neighbor. So this helps to just, this is a way of getting the list of adjacent vertices. This can also be useful when you want to do a page rank. You just know the adjacent vertices to a particular vertex. It's very useful. Another one is collaborative filtering. So what this does is it fits a model. It tries to compute a model to estimate a user's rating for an item, usually an item they've not rated before, giving ratings for other users and items. So it tries to, this is sort of like a predictive algorithm, tries to tell what is a user likely to rate this based on other ratings. This can be useful for things like Facebook ad, Google ad, things like that, Netflix. Trying to determine, okay, how is this user likely to interact with this? How are they likely to rate this based on their previous ratings for different other products and based on other users too. It does this using matrices, so it tries to solve the minimization problem. So R represents unknown ratings. Um, so just having that problem would help you understand collaborative filtering for a specific user. So in conclusion, computer architects shouldn't, while these are representative applications that we've talked about search, talked about caching, we've talked about graph analysis, we've talked about map reduce. So these are representative applications, but computer architects shouldn't, like we mentioned maybe in the introduction, we shouldn't concentrate on using this to understand the inner workings of a data center application, because like we mentioned before, this is because of the numerous abstraction layers that don't really give us the full story. What you want to do is you want to register the area of interest you want to study and concentrate on that. Another thing we have to understand is when you're benchmarking data center workloads, the type of data you put in it and the type of computation are very important than whatever benchmarking algorithm you're running and the run system for that computation. So it's the type of data. So if some data easier to pass through than others. So you have to take that into consideration when you're benchmarking a data center application. Thank you.